Alright everybody, welcome back. In this video we're going to look at the last two examples from the Power Series 2 lesson. We'll start with example 3 here. Find a power series that represents the function f of x equals 8x squared over the quantity 1 minus x to the third power. What do you think the interval of convergence should be? Okay, so first of all, when I'm trying to decide how to get this series, I first look at the denominator. It's the quantity 1 minus x to the third, and knowing the way that, differentiation works, I'm going to start out with the series 1 over the quantity 1 minus x, because that's going to be a function that when I take the derivative of it a couple of times, will end up with a quantity 1 minus x to the third in the denominator. So if I take the derivative of this, it's going to be what? Let's see, this is 1 minus x to the negative 1. So the derivative of this is going to be negative 1 times 1 minus x to the negative 2 times a negative 1 for the derivative of the inside. So the derivative of this is going to be just 1 over the quantity 1 minus x, quantity squared. And then the derivative of that, if I take the derivative of that again, that's quantity 1 minus x to the negative 2, so this is going to be negative 2 times the quantity 1 minus x to the negative 3 times the derivative of the inside. So the derivative of this is going to be 2 over the quantity 1 minus x to the third. And then to get the series that I want a series for 8x squared over the quantity 1 minus x to the third. All I'm going to do is take this third series that I find and multiply it by 4x squared. And that's going to give me the series for 8x squared over 1 minus x to the third. So here we go through this process. We start with our original series. We take the derivative of that to get the next series. So that's going to be 1 plus 2x plus 3x squared plus 4x to the third n times x to the n minus 1 for our general term. And I'm going to readjust my general term after I'm completely finished getting my new series, instead of doing it at each step. And now I take the derivative of that to get the series for 2 over the quantity 1 minus x to the third. The derivative of this is going to be 2 plus 6x plus 12x squared plus what's the next one? 5x, 20x to the third. And the general term is going to be n times the quantity n minus 1 times x to the n minus 2. And now, in order to get my last series, all I did was multiply everything by 4x squared. So this is going to be 8x squared plus 24x to the third plus 48x to the fourth plus 80x to the fifth plus come on, change over. There we go. Plus 4 times n minus 1 times x to the n. Now I want this term right here to be my 0th term, and right now it's my second term, so I'm going to add 2 to every n expression in this series, and that's going to get me where my general term matches up, that my first term in this series is the 0th term. So this is going to be 8x squared plus 24x to the third plus 48x to the fourth plus 80x to the fifth It's 4 times the quantity, and I'm going to add 2 to all of the n expressions here in my general term. And that gives me my series for 8x squared over the quantity 1 minus x to the third. Now, as far as the interval of convergence of the original was from -1 to 1. And every time I take the derivative, it's still going to be an interval of convergence based off of that. And multiplying the numerator by something, again, doesn't change the interval of convergence. So I expect that the interval of convergence for this is going to be from -1 to 1. The question is, should I include either of those? And given the nature of these terms in the series, think about substituting 1 into this series. The terms are just going to grow greater and greater, so I shouldn't be including 1 in my interval of convergence. Now, if I have -1 in there, again, it doesn't look like the partial sums are going to converge. So I think, I'm not going to do any in-depth analysis, but I think that this should be my interval of convergence. Alright, and like I mentioned in the last video, we're going to talk a whole lot more later on about how we actually determine whether an endpoint of an interval of convergence is included or not, strictly mathematically. Alright, so here we go. Example 4. Find a power series that represents 1 over the quantity 1 plus x squared on the interval of convergence from -1 to 1. We know this series. We know 1 over 1 plus x is 1 minus x plus x squared minus x to the third plus -1 to the n, x to the n. And so to get the series for 1 over the quantity 1 plus x squared, all I'm going to do is substitute an x squared in here everywhere. So my series for 1 over 1 plus x squared is 1 minus x squared plus x to the fourth minus x to the sixth, etc., etc., x to the 2n. So there's my series for 1 over 1 quantity 1 plus x squared. Now, part B. Using your result from part A, find a power series that represents the arctangent of x on that interval of convergence. Well, you should recognize that the quantity, or 1 over the quantity 1 plus x squared, is the derivative of the arctangent. And so, to get the series for the arctangent, we're just going to take the integral of the series that I've highlighted above. So I'm going to take the integral term by term. That gives me x minus x to the third over 3 plus x to the fifth over 5 minus x to the seventh over 7, etc., etc. -1 to the n, x to the 2n plus 1 over 2n plus 1 as our general term. Come on. What just happened there? Whoa. I don't know what I just did there, but that was pretty cool. Oh, I guess I went back a page. I don't know how I just did what I just did. I must have clicked on something weird. Alright. So there's our series for the arctangent of x. Now, what we're going to do next is we're going to look at this. Graph the first 4 partial sums on our graphing calculator. Do the graph suggest convergence on the open interval? So we're going to compare the graph of the arctangent to the graph of the graphs of the partial sums. So here's arctangent of x. And our interval of convergence is from -1 to 1. So I'm just going to do a quick test run here. And we'll graph this from -1 to 1. And my y values are probably going to need to be bigger. No, those will work. Alright, so there's what arctangent of x looks like. And so now let's compare this to the partial sums. And so I'm going to graph the first partial sum, x, and I'll make it thick. And so we look at the graph, and it looks like that does a reasonably good job. You know what, let's go back out to a standard window, just so we can see, divergence between this. There we go. There's the first partial sum. Let's hone the window in a little bit for x values. Let's go from -2 to 2. That way we'll be able to see let's take a look at what that looks like. We want to be able to see some difference here. There we go. That looks like a good window for us. Alright, now let's put in the next term to get the next partial sum. We're going to subtract away x to the third over 3. And now we'll compare those graphs. And you see that it does a slightly better job of approximating the curve. And now let's add in our next term, x to the 5th over 5. There's our original, and every time we do this it gets a little bit more of the curve. And you see that the question asks, do the graphs suggest convergence on the open interval from -1 to 1? You bet. Do I think that the series for arctangent of x converges at x equals 1? Let's go back to our graph here. And if you look at this curve at 1, you see it's pretty close. I would think, based on looking at this, that yes, I think that this does converge at x equals 1. And in fact, we could confirm that by trying to see, is the arctangent of 1, is that equal to 1 minus 1 to the 3rd over 3 plus 1 to the 5th over 5 minus 1 to the 7th over 7. Do I think it converges? Yes, I think it converges. In fact, I know it converges. But we'll talk about that more later on. We're about out of time for this video, and thankfully we're done. So see you guys next time. Have a great rest of your day, and enjoy yourself.